Hello guys, it's Mr. K, and today I'd like to talk to you about ions and ionic bonding. But first I'd like to go back to the basics of the structure of an atom and go back with you through how we can work out the number of protons, neutrons and electrons, or the so-called P and E of an atom. So as you may remember, each atom has two numbers associated with it. Its mass number and atomic number. Mass number is the larger one, usually in the top right corner, and the atomic number is the smaller one, usually in the bottom right corner. So if you're trying to work out the number of protons and electrons, it's quite straightforward. It is the atomic number that tells you how many of them there are. So using the example of potassium, potassium has the atomic number of 19, which means it has 19 protons, 19 electrons. If you try to work out the number of neutrons, however, what you have to do is you have to use both mass and atomic number. You simply take away the atomic number from the mass number and it tells you the number of neutrons, which in this case 39 minus 19, and that gives you 20. So what you could do with these numbers is that you can maybe try to draw the electron structure for your atom. So we'll go back to the example of potassium, and as you know, it has 19 protons and 19 electrons. So what you need to know in order to be able to draw the electron structure is a couple of rules for the electron shells. So the first electron shell, which is the one closest to the nucleus, takes 2 electrons. The second and third can take 8 each. And for your GCSE, what you need to know is that any additional electrons after that point go onto the fourth shell. So it's quite straightforward with your potassium. The first 2 electrons go on the first shell, 8 electrons on the second shell, 8 electrons on the third shell. So in total, we have 18 electrons. So that means we have one more to draw. So that means the 19th electron, 1 electron, goes on the fourth shell. So with that out of the way, we can actually start talking about ions. So in normal circumstances, atoms have an equal number of protons and electrons. As I told you before, it's decided by its atomic number. But in certain cases, atoms can gain or lose electrons and therefore become charged. It's really important that you remember that it's just electrons. They cannot gain or lose protons, okay, and it's simply based on where the protons and where the electrons are in an atom. So protons, as you know, sit in the center of an atom alongside neutrons. We call this area the nucleus of an atom, and electrons just orbit around. So based on how far away from the nucleus they are, it's actually relatively easy to gain or lose electrons. Remember, electrons have a negative charge, protons has a positive charge. So what could happen is, for instance, we can take away an electron. In this case, the atom becomes positively charged. So if you lose a negative charge, you become positive. In this particular case, since we only had 1 proton and 1 electron to begin with, this was actually a hydrogen ion. So if we take away that electron, we're going to end up with a positively charged hydrogen ion. So as you know, there are different types of ions. Ions can be positive or negative. And even within, let's say, the positive ions, they can be a single positive, double positive, or a triple positive. Same with the negative ions. So it's actually quite straightforward to work out which element forms which ion. Now, if an element is in group 1, it generally always forms a single positive ion. Now, why is that the case? Well, the group 1 elements, the alkali metals, they have 1 electron in the outermost shell. Generally, most of them need 8 electrons in the outermost shell, except for lithium, which only needs 2. But we use what's known, or what I call, the rule of proximity. So you look at what's easier to do. Since elements aim to have a filled up outermost shell, what's easier? Is it easier to lose one excess electron, or is it easier to gain additional 7 electrons to have the outermost shell filled in? The answer is fairly simple. It's easier to lose one, and that's what they do. Group 2 elements, they form a double positive ion. Same rule applies. Since they have 2 electrons, is it easier to gain additional 6, or is it easier to lose those 2 electrons from the outermost shell? So they lose 2. Group 3 elements, triple positive ions. As you can see, those are generally all metals. So we technically pretty much always say that metals form positive ions. We also have some groups, some compounds, such as ammonium, which isn't quite a metal, but it also forms a positive ion, a single positive ion. Same rule applies for negative ions. Fluorine, for example, it's in group 7. It has 7 electrons on the outermost shell. So what's easier? Lose 7 electrons or gain 1 additional electron? I guess the answer is quite straightforward. Gain 1 more electron. So it forms a single negative ion. Group 6 form a double negative ion. Group 5 form a triple negative ion. And then we have 5 more of groups that you just have to learn for GCSE because they are important. The nitrate, which is NO3, forms a single negative ion. Sulfate, SO4, double negative ion. Phosphate forms a triple negative ion. Hydroxide, single negative. Carbonate, double negative. You just have to try to remember these, but for the actual elements, you can look them up in the periodic table. Group 1, single positive. Group 2, double positive, and so on. Now, there is also something that you should try to remember, is that when an ion is positive, we call it a cation, and when the ion is negative, we call it an anion. That will come handy, but a little bit contradictory when we'll get to electrolysis, but that's going to be in a different video. So now we can actually move on to ionic bonding, and for that I'd like to use a simple animation of Johnny the chlorine, who happens to be in group 7, which means he has 7 electrons in the outermost shell, and that's where he sits in the periodic table. So if Johnny would like to get a full outermost shell of electrons, what this means is that he has to find a partner that would be willing to give away that 1 electron so he can have this outermost shell completely filled in. So Johnny meets a friend, Sophie the sodium, and Sophie the sodium is from the group 1, so it only has 1 electron in the outermost shell, but unlike Harry hydrogen, this electron is quite far away from the nucleus, so Sophie is actually quite happy to get rid of that electron so she can have a completely filled in outermost shell as well. So Johnny agrees, and they form what's known ionic bonding. So what happens there is that Sophie, the sodium, gives away that 1 excess electron, which is now accepted by Johnny, the chlorine. So what happens there is that chlorine becomes a single negatively charged, whereas sodium becomes single positively charged because there was that exchange of 1 single electron. But what this means is that both of them have their outermost shell of electrons completely filled in, and we call this an ionic bonding. We can look at some other examples, for instance magnesium and chlorine, that will form magnesium chloride. Now what's interesting is that you can use the knowledge of the ions, you know, the table that I've shared with you earlier, to help you work out the formula of your compound. So magnesium is in a group 2, which means it has 2 electrons to give away. But chlorine is in group 7, which means it can only accept 1 electron. So what this means is that for each magnesium atom, we need 2 chlorine atoms. Magnesium gives away 2 electrons, each chlorine can only accept 1. So that means that our magnesium is going to form a double positive charge, so Mg2+, and each of our chlorines is going to form a single negative charge. But because there are two of them, it's all balanced. So when you're looking at ionic bonding, you have to balance the charges. Balancing the charges will help you work out the formula, which in this case will be MgCl2, 1 magnesium, 2 chlorine atoms. You can look at another example, for instance, calcium oxide. So calcium and oxygen. Calcium is in group 2, which means it also, just like magnesium, has 2 outermost shell electrons. Oxygen is in group 6, which means it has 6 electrons on the outermost shell. So it's actually a fairly straightforward example because calcium gives away 2 electrons which can be accepted by an oxygen. So in this case, it's a fairly straightforward example. It's only 1 calcium, 1 oxygen, CaO, with calcium becoming Ca2 plus, oxygen becoming O2 minus. So, in summary, ionic bonding is generally the bonding between a metal and a non-metal. We say generally because, as you remember again from the table I shared with you earlier, you can have the groups. For instance, you wouldn't quite call ammonium, which forms a positive ion, a metal, and then you've got some other groups such as phosphate, nitrate, which form the negative ions. They are not an element per se. But generally, when you're looking for whether there is ionic bonding, you look at whether there is both a metal and a non-metal in the structure of that compound. Now, one of the atoms, generally the metal, gives away the electrons which are accepted by the other element, generally the non-metal. So using our example again of sodium and chlorine, we know that sodium is in group 1, so it has 1 electron on the outermost shell. Chlorine is in group 7, which means it has 7 electrons on the outermost shell. So what happens there is that sodium gives away that 1 electron and it's accepted by the chlorine. So we have sodium Na plus and chloride ion Cl minus. Okay, now a bit about the properties of these ionic bonds. They are strong bonds because they are formed by the forces of attraction due to opposite charges. When you think about it, it's kind of like with the magnets, with the north and south poles. The opposite attracts. So it's same here with the charges. The opposite charges attract one another. So the sodium and chlorine here would be attracted by the strong forces due to the opposite charges. And these types of bonding tend to form what's known as giant ionic structures. For instance, our sodium chloride, you know, the salt crystals, which have high melting and high boiling point. All right, thank you very much for listening. And if you have any questions, any other suggestions, please let me know in the comments below.